Yeah, hi all together. This is the third lecture on 3D coordinate systems. The last lectures we have looked into two-dimensional motions and looked for concatenations and representations, and we will now start with three-dimensional transformations. Three-dimensional transformations usually consist of translations, rotation and scales, and the most complicated part of these motions in 3D are the rotations. And therefore we will discuss rotations first, that we can then easily use them afterwards in the context of motions or similarities. Today I will give you an overview and we'll talk about rotation matrices and a representation using angles. So why are rotations important? Because of course there are already many applications for rotations only. For instance, if you have a total station, you need to know the direction and the upward angle, or you have a gyro measuring in three directions the angles, or you have antennas which you want to level, or you want to determine or describe the Earth rotation, which is then just a rotation, or you just want to describe the attitude of an object without referring to the translation part. Of course, the rotations are part of motions and similarities, and these are the mainly part which is non-linear, and therefore, of course, it's more demanding than the other part. So what I want to do in the next few lectures is talk about representations, then how to concatenate rotations based on their parameters. Then we will talk about small rotations, especially we have a look at the differential equation for a motion of a point. And the main part is about uncertainty of rotations, which require that we know how to describe small motions, small rotations. And then finally we would like to know how to derive rotations from pairs of directions. So if you have given several points on the sphere, before and after rotation, we want to know how to derive the rotation from these observed points. So generally we have a definition which we already discussed in the context of groups last time. Rotations are linear transformations in n-dimensional space which have to fulfill two constraints. First, they need to be orthogonal. That means the transposed is identical to the inverse, and they have to have determinant 1, which excludes mirroring. You could also say rotations are all those linear transformations which preserve distances between points and one point, or especially the point of origin. We will discuss several representations because each of them has special advantages and disadvantages. Of course, we will start with representing a rotation by a 3x3 rotation matrix. Then we will see that it is easy and very intuitive to describe rotations by three angles around the three axes. Then we will see that there is a representation which is based on the direction of the axis and a rotation around this axis. Then there is a mathematically quite interesting definition using an exponential of a skew matrix of a 3 vector, which is the rotation vector, which is the product of the direction of the axis multiplied with the angle. And then we have a group of three representations, mainly based on what is called quaternions. These are 4 vectors. We will see these are quite interesting because they don't use trigonometric terms. And there are two special forms which we have to look at in the Rodriguez form and the Cayley representation. So let's start to look at the matrix representation of rotation. So we have a rotation matrix which with its 9 elements, and we can either group them in columns or in rows. So we have 3 columns and 3 rows. And now, because we have this constraint that the transposed multiplied with the rotation is the unit matrix, we see that the columns if we multiply them with itself, that means taking the dot product or taking the length, we have the following 6 constraints. So if we take the diagonal elements of this unit matrix, we get the length of C1 should be 1, of C2 and of C3. That means the columns of the rotation matrix are unit vectors. And the second is, these unit vectors are orthogonal with respect to each other. That means because we have the off-diagonal terms of the unit matrix being 0, we have the dot product between Ci and Cj is 0. So these are 6 constraints. Because of symmetry reasons, of course, we also have C2 multiplied with C1 is 0, so we actually only have 6 constraints. So this means this representation with the rotation matrix is redundant. So we have 9 numbers to describe the rotation matrix, but we have 6 constraints. So the rotation in 3D has 3 degrees of freedom. That means actually we would only need 3 parameters. We will come back to this numbering at several places within the next lectures. Now let's assume you have given the 9 elements of a rotation matrix, let's say with 15 digits, between -1 and +1. The question is, how can you interpret these elements? So let's start with what the columns of this matrix mean. So we have the 3 columns of the rotation matrix. Now let's assume you multiply the rotation matrix with the unit vectors EI, A1, E1, E2, E3. So let's assume start with E1, that is 1, 0, 0. If we multiply the matrix with 1, 0, 0, we obtain the first column vector. That means this of course is valid for the other elements also. That means the column vectors of a rotation matrix are the images of the unit vectors of the coordinate system. So let's assume you have the tripod with the x, y and z axis and you rotate it around the origin. Then you get another triple with 3 unit vectors orthogonal, and these unit vectors are the columns of the corresponding rotation matrix. Now let's look at the row vectors. To do the same thing, the same argument with the row vectors, we have to transpose it. So if you multiply the unit vector from left with the transposed rotation matrix, then the first column of this transposed value is the first row of that matrix. That means if we multiply the unit vector EI with the transposed rotation matrix, we get the first row. So in general, we see that if we just put the R transposed on the other side, we see that EI, the unit vectors, are the rotated row vectors. That means actually the EI, the unit vectors, the basis vectors, are the maps of the row vectors of the rotation matrix. Now we go a step further and look for the individual elements. So the rotation matrix has 3 by 3 elements, and each of these elements can be written in the following form. Let's assume we take the rotation matrix in column way, that means C1, C2 as columns, and multiply it with the unit matrix. Of course, this doesn't change anything, but we have here 1, 0, 0, etc. And if we then look at the individual elements, we see that the first element is E1 transpose C1, or the dot product of E1 and C1. And this is valid for all the other 3 by 3 elements. That means each element is the dot product of the unit vector, of the basis vector of the coordinate system, multiplied with the column. Now the columns are the images of the unit vectors, the basis vectors. And both vectors E and C are unit vectors. That means what stands here is the cosine of the angle between the original basis vector, number 3, and the rotated second vector, that means the second column of the rotation matrix. That means this matrix contains the cosine of all angles between the original coordinate system and the directions of the rotated system. This is the reason why we could also write it in this short form. So the rotation matrix consists of these 3 by 3 elements, which are the inner products of the unit vectors multiplied with the column vectors, or which are the cosines of the angles between the basis vectors and the columns of the rotation matrix. That means the rotated vectors. That's the reason why the rotation matrix in some contexts are called direction cosine matrix, because it contains the cosines of the directions of the matrix before and after the rotation. So what does this matrix representation has as properties? So it has got some advantages. It's of course directly useful for rotating points, because we just have to multiply the point with the rotation matrix to get the rotated point. The second is it's the best exchange format. So if you send somebody a rotation, please send him the rotation matrix, but add an example. Why? Because the other one, the recipient of the mail which you send, should know whether this is an active or a passive transformation, and that means whether it's a rotation or it's inverse. So I have to describe what you actually mean by it. And this is, of course, useful with an example with some text around. And then there are quite some direct solutions for determining the rotation matrix from some given entities. They directly lead to a rotation matrix. And these direct solutions are important because if a solution of a problem is direct, we mean that it works without any iterations. Of course, there are disadvantages. The rotation matrix is a redundant representation. That means we have 9 parameters, and if we do estimation and we would like to estimate these 9 parameters, we have to impose the 6 constraints, which of course makes it a little bit awkward to do some least square solution. And there is no immediate interpretation if you have an instrument which has certain axes around the parts of the instrument are rotating. That's the reason why there are other representations. So let's start with Euler angles. Euler, already in the 18th century, proposed that you can describe a 3D rotation by 3 rotations around 3 axes. So let's look at this animation taken from Wikipedia. So you first rotate around the z-axis, like here. Then you rotate around this x-axis, the y-axis, like here, and then you rotate again around the rotated z-axis. So you first take the z-axis, then the x-axis, and then the z-axis again, and you have 3 angles. And because you describe the rotations in the local system, that means after each rotation, you are able to describe a general rotation. So this is the reason why it's useful to look at the representations of rotations using angles. So in general, not all applications, not all sequences of rotations with 3 angles use the sequence ZXZ, but it can be any 3 axes, of course not the same all the time. So if you have 3 rotations around 3 axes, you usually say these are Euler angles in a general sense. You could also say in 3D that is a rotation within a plane. So if you rotate around the x-axis, let's say the x-axis goes upwards, you rotate in the YZ plane. And this is of course valid for the other axis too. And the question is, of course, is it better to describe rotations in 3D around 3 axes or within a plane? Does it also hold for 2D? Does it also hold for 4D? Whatever this means. And think about this. The next thing is that if we don't standardize the sequence of these three axes, we have different options for the sequence. So Euler proposed first z, then x and z in the local system. Then Ted and Brian proposed to rotate around the x, y, z in the original system. And now the question is, how many other possibilities would you have? And you can imagine this will be much more than a handful. In all cases, we assume that we follow the right-hand rule. So if you have a rotation axis, x, y, or z, and you rotate around this axis along your fingers, then in the direction of your fingers, then this is a positive rotation. This is bad because if you would have a left-hand rule, you could, as a right-hander, do writing at the same time while doing such a demo. The naming of these rotations depends on the application. And one important application is if you have a moving object like a car or an airplane, then people don't talk about x, y, z because this is not clear what x, y, z is, but it's clear that if you have a moving plane and it rolls, you mean it goes around the flying direction. Then you have the pitch, which tells you whether the airplane goes upwards or downwards. And then you have the yaw, which says whether you go right or left. So you actually get these three namings for the different angles. I have written here down the names in German. Of course, it's interesting what happens if the airplane goes upwards. That means it makes a loop. What happens with the naming of these axes? Do you refer to the original system or to the system in this local frame? Now let's start to do some algebra. We use the following convention. So if you have a rotation around the axis I, 1, 2, 3, or x, y, z, with some angle alpha, I write this in this form that you have a rotation matrix with this index I around the ith axis with some alpha, and if you have I, you rotate in the yz plane. If you have y, you rotate from z to x, and if you have I equals 3, you have, that means you rotate about the third axis z, you rotate from x to y. So these are the conventions. So let's look at the individual rotations in detail. So let's start with the basic rotation number 1. This is the rotation around the x-axis, the first axis. So actually you can imagine you have an object here with a coordinate system attached to it. Let's say you have the x, y, z of my hand, and you rotate around the x-axis, so you have this type of rotation from here to here. So the y-axis of this object is moving here, the z-axis is moving here. Now, if you look at the coordinates of some point on this object, of course the x-coordinates are not influenced by this rotation. And if we now look at the y coordinates, we see let's say we assume the point sits here and it rotates here. So this is the first position, that's the second position after the rotation. You see we have the same rotation as we know from our 2D case in the yz plane. That means the y coordinates are a little bit diminished by the cosine and a little bit more diminished by depending on z. So you have a minus sign here. And again, you have a rotation matrix, a 2x2 rotation matrix with cosine on the diagonal and sine on the off diagonal, and the minus here. And if you write that down in matrix form, you can arrive at this rotation matrix. So here you have the 1, the x-coordinates don't change, and here you have a classical 2x2 rotation matrix with the angle alpha with the minus sign at this place. Now let's look for the rotation around the y-axis. What happens here? So again, we have the rotation around the y-axis. That means we have such a rotation, if this is the y-axis, we have here the rotation in this way. Now what can we say? Certainly that the y-coordinates don't change. What happens with the z-coordinates? We have here the z, a point on the z-axis, and it diminishes because of the rotation. So we have here the cosine beta. And if you have a point here, it diminishes even more because it has a positive x-coordinate. So we have the minus sign at this place. So if you put this equation into a matrix form, we have again the 1 at the 2, 2 element and a rotation matrix with cosines on the diagonal and sines on the off diagonal, but we have the minus sign at this place. Last case, basic rotation 3 around the z-axis. So we have a rotation around the z-axis, which means the object rotates this way, like my hand at the moment. So a point moves from here to here, and from here to here. You see, this is exactly what we did in 2D in the xy plane. So if we do a rotation in the y plane, xy plane, that's the same as if we would do a 3D rotation around the z-axis. So this is one, the z-coordinates stay, and we have here the cosine, the rotation matrix for gamma in the classical form with the minus sign at this place. Okay, these are the individual rotations, and now we want to concatenate them. So let's assume we have an active rotation. That means we talk about the rotation of some object, and we describe the angles around the axis in the original system. Then we have to multiply the matrices from the left. So we start with the rotation 1 with alpha, around the second axis with beta, and then the third axis with gamma, and the multiplications are from the left. Now we take these 3 matrices which we just derived and multiply them, and this gives an awkward expression. That's it, the result. That's a 3 by 3 matrix which depends on the 3 values alpha, beta and gamma, and obviously contains the sines and cosines of these 3 angles. Now don't try to remember this, but we have to remember a little bit about the structure. We see that the angle beta occurs as only angle in this expression. And then we have products of 2 trigonometric terms in the corresponding row and column. And the other 4 elements are sums of products of cosines and sines. We will use this information about this basic structure later. Now let's assume we have an active rotation in the local system. That means we first rotate around the first axis, then the second axis is already rotated, then we rotate about this local y-axis, then also the z-axis is moved again, and then we rotate around this z-axis. And if you then write this down, we need to do the multiplications from the right. And of course this will lead to a different matrix. This is shown here. Similar structure. We have 1 element depending on 1 angle. The rows and 2 columns are products of sines or cosines. And the other 4 elements are sums of products of cosines and sines. Now, what happens if we have a passive transformation? Now, this is easy now, after that what we have discussed last time. It's just a transpose of the corresponding active transformation. So, a passive rotation with respect to the, if we describe it in the original system, is nothing than the inverse or transposed of the matrix which we know from case A. So if we take the rotation matrix of A, transpose it, we get the rotation matrix for case C. So If you want to know the Kc, you'd have just to take this matrix and transpose it. The same is of course valid if you have a passive rotation of a coordinate system and describe the consecutive rotations in the corresponding local systems. Then we have to take the transpose of the rotation matrix B. Okay, this is easy to remember in contrast to these algebraic expressions here. So, but this is the definition, and you could of course program this in this way, and so you have a routine for the individual rotations, and then you concatenate them in the way which you need. Now let's assume you have a rotation matrix, and you would like to know what are the three angles alpha, beta, and gamma. There's a problem. We talked about three angles alpha, beta, gamma. Now, is it this matrix? Is it this matrix? Or is it this matrix? Or is it this matrix? Or is it one of these original Euler systems where you first rotate around z, then around x, and then around z? That means if you don't know this, you are not able to derive the angles. So you need to know the algebraic structure of your rotation matrix. So if you send somebody the rotation matrix, you also have to tell him the algebraic form of the rotation matrix. Or other way around, if you send a rotation matrix and you want to know the alpha, beta, gamma in your own system, then you need to know the structure of your own system. And then you can derive the rotation angles. Now, we have already seen that these rotation matrices all have a special structure. There's always one term only referring to one angle. So, for instance, we have a sine beta term. The question is this useful for this angle? In the first idea, yes, of course. Then, of course, the corresponding rows and columns. Let's just have a look. So we have here the sine beta, and the column contains the angle alpha. If we know beta, we can calculate alpha, and if we know beta, we can calculate gamma from these values. So this should be doable. So in all cases, we would like to derive angles from sines or cosines, and there is a heavy warning. Don't use the arcus cosine or arcus sine of some value in order to determine the corresponding angle. Why is this so? Let's assume we have a small angle, and we want to determine the angle from the corresponding cosine. So let's assume we have a computer which works with 10 digits. In Maple, you can define how many digits are used. So I used the case with 10 digits. So if you determine the cosine of 0.01, you get this expression with 10 digits. The corresponding sine expression is this one. Now, let's assume you call the arcus cosine of this numerical value. Then what you get is 0.01, which is fine. But if you go a little bit further, within the 10 digits, you get 167 at the last 3 digits. That means the use of the arcus cosine leads to an inaccuracy, a numerical inaccuracy of your calculation. Why is that so? So have a look at this graph where you see here the cosine function. And here is the angle, and here is the cosine. Here is 1. And now let's assume you have the cosine of an angle, like this here, 0.85. Then you have to go to the right and to the down and get the angle. Now let's assume you have an angle which is very small. Then you have to intersect this cosine function with a horizontal line, and the angle between the cosine function and this horizontal line will be very, very small. That means the position of this intersection point is very uncertain. So that is, so to say, the visual explanation why this happens. Now, if you take the sine and the cosine and use the two-valued arcus tangens function, you have no problem. So, use the two-valued function for the arcus tangens in order to determine angles in all cases. So let's have a look what happens. Let's assume we have given a rotation matrix with the numbers, and we would like to derive the three angles, and we know that it is the rotation matrix has this structure. That means this is a definition how the rotation matrix depends on the three angles. And we want to have the numerical values for alpha, beta, gamma. Now let's have a look at alpha. Where is alpha? Alpha stands here and here. In both cases multiplied with cosine beta. So we could take this value with the sine alpha, and this value with the cosine alpha, and put it into the arcus tangens value with the sine part and the cosine part. That means the alpha is the arcus tangens of the two-valued arcus tangens of R3, 2 and 3, 3. Yeah, so this is the. Now we can do the same for gamma. You have here the cosine gamma and here the sine gamma. That means we, in a similar way, get the arcus tangens of R21 with the sine and R11, which is the cosine part. And how do we do this with the beta? We don't have the cosine beta directly, but we have here the sine. So we start with minus R31. And if we take these two values, take the squares, sum them, and take the square root, we get the following. So we take this, we first see that the cosine can be taken out, so it will be cosine square of beta multiplied with the sum of sine square of alpha plus cosine square of alpha. So this is 1, so what stays is cosine square beta, and if we take the square root, we get the cosine. So this way we are able to derive the beta with the arcus tangens 2 function from minus R3, 1, and the square root of the sum of these squares. Okay, this looks nice. Does it always work? No. Because if cosine beta is 0, then there will be 2 zeros here. Also, there will be 2 zeros here. That means we cannot determine alpha or gamma. We can determine beta because there stands a 1 and 0, 0, so there will be no problem. Arcus tangens of 1, 0 is determinable, so this is well defined, but we cannot determine the other two. Now, the second thing is that we assume that here the square root is taken as the positive value. What would happen if we take the negative value? What would change? So we have to have a look at this. So let's start with the case that cosine beta is 0 or beta is plus or minus 90 degrees. So what happens? In the matrix, we will have a 1 here and zeros here and here and here and here. Now what happens here? We have the sine of beta is 1. And then we have here cosine gamma times cosine alpha plus sine gamma sine alpha, which is the cosine of the difference of gamma and alpha. So we have here this expression. And similarly, we have here the sine beta is equals 1. So we have here sine gamma cosine alpha minus sine alpha cosine gamma, which means this is the sine of the difference. And similar for the other cases. Now what happens here? We have a rotation matrix. We have here the cosine on the two diagonals, and we have the sine on the main diagonal. That means this is a rotation matrix, but depending on the difference of gamma and alpha. So if we want to determine alpha, this doesn't work. But if we only want to determine the difference, this works. That means in this case we are not able to determine all parameters. This is singularity, which we will find often in these situations. So let's assume, to make this visual, we have an aeroplane moving in this direction. Internally it measures with a gyro the three angles around the three axes. So if this would be the first axis, we have a gyro, the green gyro, which works in this direction. The y around the pitch is around this axis, and the yaw is around this axis, so there is no problem. Now let's assume the aeroplane makes a looping and is upwards. Let's assume the gyro goes with it and rotates also by 90 degrees. That means the green and the blue gyro are in the same plane, measures the same thing, and we have no idea how to know the rotation around the original roll axis. That means we lose the measurement of one angle. That means, as a practical consequence, it is not possible to control the direction of the airplane anymore, because we don't have all measurements. We only have two measurements and not all three. So this is called the Gimbal Lock, because the control of the aeroplane is locked. So what are the properties of this representation? We talk about singularities, discontinuities, and uniqueness. So what we learned is that there's a singularity, namely the Gimbal Lock. This holds for all cases where we have three Euler angles. In all cases will this happen. Then we have a discontinuity. This is the same as if you describe directions in the plane. You measure directions, let's say, between 0 and 359 degrees. And if you are larger than 359 degrees, you go back to 0. So there's a discontinuity, even if you go from minus 180 to plus 180 degrees. There's a discontinuity in all cases. Then the definition of the rotation matrices is not unique. That means if you have rotation around the axis 1, 2, 3 with alpha, beta, gamma in this sequence, you will get the same rotation matrix algebraically if you rotate the first axis, if you add 180 degrees, if you take beta minus the second angle around the second axis, and if you add 180 degrees to the third angle around the third axis. So you have an ambiguity in the definition of the three angles alpha, beta, gamma. That means the cosine of the beta changes the definition of the angles. We use the positive square root, as you remember. That means we assume that the beta is in the range of minus 90 to plus 90 degrees. We will see later that all representations which rely on three parameters show such types of such defects. So in general, if you have a general rotation, these representations are not useful estimation unless you can know that the angles are small, let's say. And the angles are not useful for exchanging 3D rotations. I mentioned this a little bit. I will repeat it once more. I asked somebody to send me a rotation. From some photogrammetric application. So he sent me a mail back with three angles, alpha equals some value, beta, gamma. I said, I don't know what the rotation is because I don't know what the definition of the rotation metric is. So I had a mail back. He sent me back, yeah, this is the classical definition. I said, I don't know what the classical definition of a rotation matrix is. What is your classical definition? And I said a mail back. And then he said, it's the one in Krau's book. And I mailed back, which of these definitions in Krauss' book do you mean? And then he showed me the equation. And I said, is it a coordinate transformation or is it a motion? So it was 3 times back and forth to find out what the rotation actually was. So avoid angles. Then you only have one ambiguity, namely whether it's an active or passive transformation, and write an example for the transformation of a 3D point that you can check whether you have done the right thing. Okay, now let's apply these rotations with angles to some coordinates representations on the sphere. So usually if you have a spherical triangle, you would have 3 points, A, B, C. You have 3 angles, alpha, beta, gamma. You have 3 sides, let's say A, B, and C. And A, in this case, is an angle, namely the angle where you see the points C and B from the origin. So it's actually this angle. So you usually use spherical trigonometry. I don't want to make a course on spherical trigonometry, but I want to show you some small example how to use the rotations for solving specific problems on the sphere. Usually we use coordinates, and you know, of course, geographical coordinates, latitude and longitude. You can imagine Cartesian coordinates in a 3D coordinate system with the origin of the sphere in the center. And you can imagine polar coordinate system. For instance, if you want to know where C is with respect to A, you could say it's in this direction and at that distance. So we will talk about geographical Cartesian polar coordinate systems on the sphere. How are they defined? Cartesian coordinates refer to the center of the sphere and are described by x, y, z. And because it's a point on the sphere, this will be a unit vector. We start with the convention that the equator plane is the xy plane and the north pole is the z-axis. So you still don't know in which direction the x-axis is here in the equator plane. And this, of course, is not good for communicating geographical coordinates. So in 1859, at the English Academy of Science, they agreed that the x direction of this Cartesian coordinates goes through the meridian of Greenwich, which is a small town close to London. So if you intersect the meridian through Greenwich with the equator, you come to this point, and the direction from the origin to this point is the x-axis. The y-axis is orthogonal, and z anyway is orthogonal. So this is a definition of the Cartesian coordinates for describing points on a sphere. The second are geographic coordinates. They only have 2 parameters. This sounds good because we only need 2 parameters. You have a surface, a 2-dimensional surface, and then you would expect that you only need 2 parameters. You will see that this will cause some troubles. So let's assume we have the origin of this geographic coordinate system at this point of the equator going through the Greenwich meridian. And you have here the point P. Then the longitude is the angle between the 2 meridians, one through Greenwich and one through P. So it's this rotation angle from here to here, or from here to here. The second is the latitude, is how much do you have to move from the equator to the point P in terms of angles. That this is this angle, and this is the latitude. So it's the angle of P with respect to the equator plane. Similarly, we can define polar coordinates. Here the Cartesian coordinates are just repeated. We have polar coordinate system, and I only walk with one specific one. Let's assume we have a rectangular coordinate system on the sphere. So we have here the north axis, which we take as reference. and we want to describe the coordinates on the sphere in polar coordinates, so we need to know the distance. That is this one. That means this is the angle between this vector and this vector. And the azimuth in which direction we have to fly. So this circle here is a great circle, the shortest distance between P and the origin. So if you would start flying here to this point, it would be best to follow this path. So these are polar coordinates in this specific coordinate system. So let's start with the first question. Let's assume we have given the geographic coordinates lambda and phi, latitude and longitude, and we want to know the x, y, z coordinates. Okay. What do we want to know? We want to know these coordinates in the x, y, z coordinate system. So what do? We take the North Pole, where we know it has the coordinates 0, 0, 1. That's the third unit vector. And make a rotation that such this North Pole moves into this point P. And then we get a rotation matrix. And we know that the third column, the last column of this rotation matrix, will be the coordinates of this point in this coordinate system. So we have to rotate the pole into P and look for the third column. How do we do this? We perform two rotations. The first one is we rotate the North Pole in a point which has the same phi as P. So let's do this rotation. So the point N moves to N prime. And then we move from here around the z-axis by lambda and get the point P. So we have two rotations, one around the y-axis by 90 minus phi. This is phi from here to here, so this is 90 minus phi. So this would be the first rotation, and then the second is we rotate by lambda around the z-axis. So we obtain the following rotation matrix. This is an active rotation, so the point moves, and we describe the rotations in the original system. So that's the basic situation. So the first rotation was about the second axis, the y-axis, with 90 minus phi. And the second rotation was about the z-axis with lambda. If you multiply this out, we get this matrix. And now we know that the third column is actually the transformed, the moved point. That means the coordinates of the points P in the XYZ coordinate. So the point P has the three coordinates P1, P2, P3, which are these expressions. So this is an explicit expression for how to calculate the 3D Cartesian coordinates from the geographic coordinates of that point. Now, let's turn the question around. Let's assume we have given the Cartesian coordinates. How can we calculate the lambda and phi from this expression? We, of course, need to have this relation. So we want to use the arcus tangens with two values. So we have to look for the sine of the phi and the cosine of the phi, and the sine of the lambda and the cosine of the lambda. So the lambda is easy. So the lambda is the arcus tangens of P2 and P1. P2 and P1. And the phi is the arcus tangens of the third value. And again, this trick with the square root of the sum of the squares. To eliminate the phi, we get the sine and the cosine here, which is here's the cosine, and we eliminate the lambda by this expression. So it's actually the square root of the sum of these two values, which leaves us the cosine phi. So we have here the sine phi and the cosine phi, we get the angle. Okay, this is fine. Does it work always? No, because if cosine phi is 0, we have a problem. What does it mean? That means we have phi is plus or minus 90 degrees. So if you are at the North Pole and want to describe the coordinates of the North Pole in geographic coordinates, you know the latitude, which is 90 degrees, but you cannot define the longitude because it's just not defined. It doesn't matter in which direction you go with the distance 0. Same for the South Pole. Okay, now we would like to have the transformation from geographic to polar coordinates. So we have this point in geographic coordinates, and we want to describe in polar coordinates with respect to this coordinate system here in OG. So what we do is to rotate the coordinate system such that the North Pole moves into this point, and then we argue with the geographic coordinates in this new system. So the z-axis moves here, the x-axis moves here, and the y-axis stays. Now what happens? The first is that the longitude in this new system is this angle, and alpha, the azimuth, is 180 degrees minus this angle. What happens with the distance? If we would have the equator rotated, it would be somewhere here. So we take the latitude and take 90 degrees minus the latitude. So we can derive the coordinates, these polar coordinates, after such a rotation. So this is the rotation which we have to describe. This is a rotation by 90 degrees around the y-axis. Now, this is the passive rotation because P is not moving. It's just the coordinate system which is moving. So we have to multiply the coordinates of P with the transposed of the rotation around 2 with 90 degrees. So we take the description of the point in geographic coordinates, so depending on lambda and phi, actually these are the Cartesian coordinates, we multiply that with this rotation matrix. You see the y coordinate doesn't change, the z coordinate gets a -1, and these two are exchanged. So we get the coordinate of P in this geographical coordinate system, Cartesian coordinate system, is minus sine phi, etc. Now, in this system, this point here has the Cartesian coordinates. And how do they depend on the geographical coordinates in this system? Oh, this is the old equation, just with all the lambdas and phi's referring to this new system G. And that means we have to determine alpha as 180 degrees minus the length in this system. So we have to find out how do we get lambda from this equation. So we have to take the arcus tangents of this and this value. That means 180 degrees minus arcus tangents of this and minus phi. This is here. And then taking the rules of the trigonometric forms, we can finally write down alpha as arcus tangents of two values of sine and cosine of the two angles phi and lambda. So this way we can derive the azimuth of this point as a function of the geographical coordinates of that point. Now we would like to have the polar coordinates, the distance. We should allow that the radius is not 1, so whether it's the Earth radius or some other radius. Of course, we have some direct, very clear solutions. So you see here the phi, which we would use, is here. And you have here the sine. That means we could use the arcosines of this expression and get the distance as radius multiplied with 90 minus this angle. This is not very good because it's unstable close to 90 degrees. We have an arcosine here. And we could also say the distance is very simple. to determine, because this D is an angle, namely the angle between this direction vector to P and to this unit vector. So we just take the dot product of the unit vector in this direction and the point, and take the arcus cosine, because the dot product is cosine the angle. So we would take the dot product of E1 and P, and this gives us this expression. Again, this is unstable for small angles, for small distances. So these are not good. These are simple equations, but these are not numerically stable for all cases. And if we do this for the case that we use the sine and the cosine, we have a look at this expression. And again, we want to know the phi from this vector. So we take the first element and take the square root of the sums of the squares of this element. So we have to take this element and the sum of square root of these two elements, and we arrive at this expression. So you see, this is useful if you have a point and you want to know in which direction and at what distance is this point from the origin OG on the equator. You can generalize this to some other point on the sphere. So if you want to know in which direction you should start to fly, if you start in Frankfurt and want to arrive in Sydney, then you can use corresponding equations which are a little bit more complicated than those, because the origin is not in this special point OG, but at some other point. So what did we see? We saw different coordinate systems on the sphere. We derived their relations using basic rotations, and of course these relations could be derived in many other ways. I don't say these are the shortest ways to derive them, but they use the material which we had. And in general, it's very useful to use spherical trigonometry and have triangles, let's say, involving the North Pole and the 2 points, and then it's easier to derive an azimuth from this way. Okay, these were the 2 first representations for rotations, namely with rotation matrices and Euler angles. And next time we look at 2 other representations, one which is called axis angle rotation. So you have an axis and a rotation around this axis with some angle. And then a mathematically appealing representation using the exponential of a skew-symmetric matrix. And we will see that these are very, very closely related. And this is the topic of our next lecture. Thank you very much for listening. Until next time.